Hello, and welcome to today's AI for Good webinar series. My name is Reinhard Scholl from the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technology. ITU is also the organizer of AI for Good in partnership with 38 UN sister organizations and co-convened by Switzerland. It is a great pleasure to welcome our sister organization in Vienna today, the International Atomic Energy Agency, which curated today's session, AI for Atoms. Before I hand over to my fellow physicist, Matteo Barbarino, who will be moderating today's session, let me review a couple of housekeeping rules. As usual, we count on your support to make this webinar an exciting experience. Your microphone has been turned off. Please use the Q&A functionality to write questions for the speakers and use the chat functionality for everything else. The speakers may either respond in real time during the session or perhaps later in the Q&A and panel discussion. And with that, I am happy to hand over to you, Matteo.
Thanks, Reinhard. Good afternoon from Vienna to all of you. I'm Matteo Barbarino. I'm the nuclear plasma fusion specialist at the International Atomic Energy Agency. And as you just heard, the IAEA has partnered with the International Telecommunication Union in the AI for Good and in the organization of this webinar on AI for Atoms. So I feel very honored to introduce Chesub Lee, the director of the ITU Telecommunication Standardization Bureau, for his opening remarks. Please welcome Director Lee.
Yeah, thank you, Matteo. Very good day, everyone. I welcome you of today's episode, AI for Atoms on AI for Good. I wish all of you have a good spirit and a good health. It's a great pleasure to welcome the colleagues of our sister organization, the International Atomic Energy Agency, curated of this today program. ITU, International Telecommunication Union, is the United Nations specialized agency for ICTs. We are global membership of 193 member states and over 900 companies, universities, and the international and the regional organizations. ITU, we are coordinates the global allocation of radio frequency spectrum and the satellite orbital positions. We develop international standards that make the communication network run. And we support countries around the world in advancing their information and communication development. We also provide AI for Good, a publishing and collaboration platform. AI for Good is not only ITU's platform, it is your platform. Everyone who can contribute on how AI can help achieve the sustainable development goals is welcome to present on AI for Good. ITU does a lot of technical work on AI and machine learning. Much of this work has been initiated by the AI for Good platform. A significant part of the technical work takes place in groups that we call, ITU call, focus groups. Open platforms, free to join, no ITU membership is required. So one of our most exciting AI work takes place in the focus group on AI health, driven by ITU, together with the WHO. The group is developing a process to test the quality of AI for health solutions so that you can trust AI solutions. We have delivered a standard tool set to integrate machine learning into 5G and future networks. We are running currently for the second year, the ITU AI in 5G challenge, a competition which draws hundreds of students and professionals to solve real problems in communication networks. We have a focus group studying environmental efficiency in view of the latest advances in frontiers, such as AI. A focus group that operates together with the World Meteorological Organization and the United Nations Environment Program works on AI for natural disaster management. We also have a focus group working to monitor and assess the behavioral performance of the AI drivers in control of automated vehicles. And we just started AI for Road Safety Initiative, established in partnership by the offices of the UN Secretary General's Special Envoy for Road Safety, as well as the UN Secretary General's Envoy for Technology. And finally, our most recent focus groups established just a few weeks ago as the Food and Agricultural Organization of the United Nations as a partner. We examine AI and the Internet of Things for digital agriculture. So now we are very happy that the International Atomic Energy Agency has joined of this AI for Good with two events. Today is AI for Atoms, and next Wednesday with AI for Nuclear Energy. We look forward to continuing of this working together to ensure that AI helps us to care for each other better and build a better future for all. I wish all of you enjoy today's program. Thank you very much.
Thank you very much, Director Lee. So now I have the immense pleasure of introducing Melissa Denike, Director of the IAEA Division of Physical and Chemical Sciences, for her welcoming remarks. So please welcome Director Denike.
Thank you very much, ladies and gentlemen, dear colleagues. It is also my great pleasure to welcome you to this webinar today, AI for Atoms at the AI for Good Summit, AI for Good Global Summit, which the two sister organizations from the United Nations system, the International Atomic Energy Agency and the International Telecommunications Union, have joined forces to realize. The webinar's overarching goal is to promote applications of artificial intelligence, machine learning, and deep learning to areas of nuclear science and technology, which target achievement of the UN Agenda 2030 Sustainable Development Goals, or SDGs, in an inclusive, transparent, and ethical way. Let me take you on a brief excursion to explain how we got here today, what's in store for the program, and what are the aspirations for the future as we move forward. So starting, how did we get here? So two recent events that my Division of Physical and Chemical Sciences was instrumental in organizing set the stage to have this webinar today. The first took place slightly more than a year ago at the 64th IAEA General Conference in September 2020 that took place in Vienna. At that General Conference, we hosted a side event on artificial intelligence for nuclear applications. So crystallizing out of the presentations given by my division, the Division of Human Health, and international experts at this event, and ensuing discussions of AI applied to novel opportunities and challenges in nuclear application areas, crystallizing out was a need for combined effort across disciplines, including means for information sharing and development activities such as technical meetings and establishment of knowledge sharing platforms to coordinate and support collaboration among cross-domain researchers. Following that event, my division organized a rather large pioneering technical meeting on AI for nuclear technology and applications. This was held last month in partnership with 6 other IAEA divisions. So the interest in this event went beyond our expectations, and over 300 participants from 67 member states, intergovernmental and non-governmental organizations were attracted. So this success sends a message of general recognition of the enormous potential of AI to promote and accelerate safe, secure, peaceful, sustainable uses of nuclear technologies, which is literally the core of our agency's mandate. Another message we received is that to do this effectively, strong international partnerships and cross-cutting cooperation is mandatory. And this is one of the reasons why we've partnered with ITU and other UN organizations in AI for Good. So what will we hear today? This webinar will cover ways in which AI can help foster innovation in nuclear science and applications in a number of SDG areas, including number 3, well-being, number 2, zero hunger, number 4, education, number 9, innovation, plus number 7, clean energy. This webinar will also explore a new domain of normative and applied ethics, lying at the intersection of AI and nuclear applications, and provide an overview of potential ways to mitigate ethical concerns. Such dialogue is of particular importance for AI applied to nuclear technologies, targeting equitable, sustainable development for present and future generations, as this has both inherent moral and risk issues. So where do we go from here? The IAEA is seeking open dialogue and collaboration with others to promote application of AI to nuclear science and technologies in order to better support its member states in the peaceful use of nuclear technologies. An example is this very webinar, which is a result of cooperation with ITU and UN sister organizations. We also hope that we can renew that cooperation in AI for Good next year. We also hope that we can work together with other focus groups to share a path to greatest impact by community building, which should include establishing an AI for Atoms knowledge sharing platform I mentioned earlier, instituting stewards and curators of databases and guardians of codes used, supporting regulation and training, and nurturing and propagating ethical guidance. So if I could make this simple and translate it using strap lines for this webinar combined with our IAEA mission, I would say we are on a path to enable AI for Atoms to support Atoms for peace and development. So we invite you to join us on this journey. In closing, a word of thanks is always due, and allow me to thank very much those on the front line of organization, people from the agency team, Matteo Barbarino, Jaroslav Pinda, Gert Diakon, and Simon Kelly, and the team from ITU headed by Reinhard Scholl. And of course, I also want to thank warmly the speakers today for sharing their expertise and work with us all. Thank you, and I'm wishing you a successful webinar. Thanks.
Thank you very much, Melissa, for your kind words. So let me thank you again and Director Lee for your time today in opening our joint event. Okay. So now let's move forward with the first talk of today's webinar. We start with AI in healthcare, support for diagnosis and treatment of disease, which will be delivered by Professor Georg Langs. Dear Georg, over to you.
Thanks. I'm just sharing my slide. I hope you can see my slides.
Yes.
Yes, perfect. So thanks a lot for the kind introduction, and thanks a lot for the invitation and the possibility to speak here. I'm really looking forward to the discussion and also to the other talks. In the next couple of minutes, I'd like to give you a brief overview of the role of artificial intelligence in healthcare, a bit about the state of the art where we are now, the next steps that are kind of now coming up and looking promising, and also what I believe is necessary in order to facilitate it and to accelerate this process. A few declarations, just a second, a few declarations. So the general role of artificial intelligence in healthcare, many people are looking at that in different areas. There is a big impact that we are seeing right now, and that I think is the one with the most mature technologies, where artificial intelligence helps us in the diagnosis and in the guidance of treatment. And that has impact on how we can deliver treatment that we have already, but also increasingly impacts the way we deliver or where we develop new treatments. So new treatment development is very often linked to the development of the corresponding diagnostic procedures that are often in turn linked to the artificial intelligence techniques that might help them. There is a role for artificial intelligence in enabling delivery where it's not possible right now, or where there is not the level of delivery of bringing healthcare, bringing diagnostic capacity to remote areas or to areas where experts are rare. And these are growing areas also all across the globe. There is definitely a role of a cost saver, which has impact because then we can use resources somewhere else for going more deeply. And I'll show a few examples for that. And one particularly exciting, I think, impact of artificial intelligence is that it is an enabler to transfer knowledge and to pool knowledge, to bring knowledge that is collected at very different centers in different geographical regions together and make them available to experts and to medical professionals and also to patients across the globe. In the next couple of minutes, I'll focus on the diagnostic part, but I hope that also in the discussion we can touch a couple of others. In the diagnostic part, the role of artificial intelligence is mainly we can view it as a prediction problem. So we would like to know what will happen to a patient, what will happen as disease progresses. And we are very often also interested what will change with that if we perform a certain treatment. So if we have a treatment, we would like to be able to predict what happens to a particular patient. And that becomes more and more relevant because more and more treatments are getting available, and we understand more and more that a single diagnosis is only really a starting point because different treatments work differently for the same diagnosis, just because of the combination of the particular stage of the disease, of the kind of the disease variant, and of the interaction between the disease and the patient. And the tool to do that, in our view, and it seems to emerge that this is a powerful instrument to help this decision and help this prediction, is to use machine learning, artificial intelligence, together with the data that we are able to acquire by imaging, but also by other diagnostic approaches like genomics, proteomics, or other clinical information that we can use. Very briefly, I think all of you know the overall principles, but basically for a machine learning algorithm, the world is a bit simple. It's basically a bunch of training examples where we have the input and the output during the training phase. Let's say, for example, an image, and we want to know if there is a lesion and where this lesion is, or what's the diagnosis. And we train the model so that if there is a new example, the model can replicate that. And that is the state of the art where we are now. And I'll show that with a few examples in the medical imaging area. And that is that machine learning is very helpful. And that is already entering clinical routine with products that have the maturity so that they are becoming medical products to detect and quantify markers that help us with the diagnosis and with the prediction. And that means that right now, artificial intelligence can fairly well segment organ, segment anatomical structures and imaging data, detect the structures, detect basically a navigation within the body so that it can say, where are we, where should I observe individual findings, or where should I observe the change of findings that happen during disease and during treatment. And that makes it a very powerful tool in giving us quantitative information about the disease and the response to treatment. And that in turn also allows us to learn from many more patients, from many more patient stories, because by these quantitative values, they become comparable and we can see patterns in larger populations. An example for a disease relevant detection problem is here in cancer, in multiple myeloma. So on the top, you see this is a patient, a full body MR and 2 cancerous lesions. And on the lower part, you see what an algorithm can detect when it scans this entire image. And what we see is, first of all, it detects the lesions, but it also detects so-called false positives. And that brings us to, I think, the 2 things we always have to solve when we bring artificial intelligence into the clinic, into the routine. And that is, we have to solve the method problem. Can we detect? Can we measure? But we also have to solve the problem of bringing it to the right part in the diagnostic workflow, in the treatment decision workflow. Where does it help and how can it shape to be helpful to the clinician? One thing that has arisen in the last couple of years and that has become very mature very rapidly is that we can use artificial intelligence not only to perform decision or to support decisions, but also to improve the quality of data. And what you see here is an X-ray, and we can use artificial intelligence to, in this case, remove occlusion so that the assessment of the lung is easier for the expert, is easier for the radiologist. And I think that's also a good illustration of a second insight that we had during the last couple of years. 5, 6, 7 years ago, a lot of the discussions were, will AI replace the diagnostic fields? We now know that that will not happen, but it will really be a tool that will help diagnostics and diagnostic experts to make better predictions, make better treatment guidance. The next step, and that is something that is enabled by artificial intelligence because it allows us to go beyond what we do now in medicine. It's not about automation, but it's about expanding our capabilities. And the reason why artificial intelligence has this potential is that the diagnostic vocabulary, the vocabulary of markers that we use in order to perform diagnosis is driven by what we see in patients, what we can observe, and what we can link to the future of patients, but it's also driven by the need to teach it to the next generation of diagnostic experts. And so there is a certain limit what we can teach, what we can explain with words, and artificial intelligence allows us to expand this vocabulary a bit because it allows us to detect other patterns, maybe subtle signatures that are distributed across different imaging or other lab and clinical values that might have predictive values. And if you again take this lens of machine learning and look at the problem, then it means that instead of looking at examples where we know what the model should predict, we just leave away the target and say the model should just look at examples and should tell us if there is any structure in these examples. Are there groups in examples that are really similar and that might stand out as particular patient groups or as particular pattern types that we see in the data, and the data might be imaging data or other diagnostic genomics, epigenomics signatures. An example for that out of lung imaging. So here we have a vast amount of different patterns that might or might not be relevant for the disease progression or the disease itself. And these unsupervised approaches allow us to look for patterns that are there and that are linked to disease progression. And that has two consequences. One is that we can then use them in order to guide treatment for individuals, but it also has, and I think that's really interesting and relevant, it also gives us a way of going back to the biology of what is happening below this imaging data, what is causing the imaging data. We can use it in order to extract pathways that are happening during the progression of the disease, during the transition from healthy tissue, in this case, to very severely diseased tissue. And if we lift that to the patient level, it also means that we can look at groups of patients. Here you see every column is a patient, every row is a visual feature that we see in lung imaging data. And we see that we can find groups for whom we did not have names before, but they are groups of very particular phenotypes that we see. And in this case, the goal was to predict the risk of acute respiratory distress syndrome. And it turns out we can find groups with particularly high risk and treat them accordingly. And again, go back to the question of why are they high risk? Where are the signatures of this high risk? And with that, I'm at the last point, and I'd like to give one example, which I think is relevant, and I think is a good illustration that artificial intelligence is not only there and can not only help us to diagnose and guide treatment, but it can also help us to understand the really fundamental biology of humans, of our anatomy, of our physiology. And I brought an example from in utero imaging. So these are prenatal MRI images of fetuses and twins on the left-hand side in the 18th and in the 28th gestational week. And we can use artificial intelligence in order to take this data, learn from this data, and derive something like a model of brain development, which teaches us about the very early and initial phases of this, I think, very exciting capability. And with that, I'm at the summary. I think what we know as the state of the art is that artificial intelligence can help us in diagnostics, in the delivery of health, in the guidance of treatment, mainly by prediction, but also by expanding our vocabulary of signatures. And one of the key, I think, enablers that can accelerate that is the capability to share and to pool data and make it available to the research community. And we're trying that. And I think that's a big boost for getting better models and understanding better how they can actually support routine. Thank you.
So thanks, Georg. So Georg is a professor at the Medical University of Vienna in Austria. I saw immediately these challenges that you wanted to highlight as they reconnect what we just heard also from Melissa's these needs for data stewardship. You highlighted data pooling and integration in treatment decision workflow. So I think we're going to be seeing this as common themes across all the other talks. Mm-hmm. So maybe we come back to this in the panel at the end.
Thank you.
So thanks for staying within your time. So let's move to the second talk, which will be given by Dr. Frank Albinet. He's a consultant, also working for the Iaea, and the talk is on AI, nuclear, and related technologies in food and agriculture. Over to you, dear Frank.
Hi, everybody. Just trying to share my screen. It should be okay. Can you see my screen?
Yes.
Yeah, super. So thank you very much, Matteo, and thank you, the AI for Good organizer, for giving me the opportunity to give this presentation on how artificial intelligence can help us in addressing the challenge ahead in the agriculture and food system, in particular when applied with or for nuclear-related technologies. So my name is Frank Albinet, and as Matteo said, I'm an independent consultant, and this last decade I've had the privilege to collaborate with the joint FAO-IAEA Division Center on Nuclear Techniques in Food and Agriculture. So in this talk, I'd like to share not only my personal view on the topic, but also to convey the discussion carried out at FAO 2 weeks ago during a week-long technical meeting on the topic. So what issue do we want to address? Based on many evidences, there is no longer any doubt that due to climate change, agri-food system sustainability and the need to make it resilient are both major issues. Obviously, this is very tempting for an engineer like me. The solution is far from being exclusively technology-centered, but nevertheless, I do believe that AI can be part of the solution. Let's look at how we could formulate the problem. On the one hand, as already experienced, but also as anticipated, climate is changing at rapid pace, and decision-making needs to be informed by data at all scales. But on the other hand, nature has its own tempo, essentially linked to seasons. And again, due to resource-intensive data acquisition processes, many systems, like for instance, the salt system, is notoriously undermeasured. So we see that data is both an invaluable asset and a scarce one. So how artificial intelligence and data science at large can help? Actually, everywhere we can get access to critical mass of data that can be leveraged with AI, and we can harness innovative data acquisition means, and we can take advantage of open data policy. So these are the three main requirements. So let me give you three particular areas where AI can make a big difference in food and agriculture. So the first domain is the calibration of analytical instruments. As already mentioned, it is often very resource demanding to estimate properties on samples, be it soil, plant, or food ones. It often requires to go to the field to collect samples, to bring those samples in labs, to use complex chemical processes. Potentially, this is a long and costly process and very difficult to scale up. So instead, using analytical instruments, such as, for instance, mini-infrared spectrometers or cosmic ray neutron sensors, calibrated through deep learning techniques and leveraging available datasets, sample properties can be predicted in a high throughput manner and often with unprecedented accuracy. So this is the first example. The second domain is data fusion, where the fundamental multi-scale nature of data to be analyzed in food and agriculture can be harnessed and leveraged. So for instance, again, the cosmic ray neutron sensors can help to bridge local measurements with global one, like satellite imagery, for instance, to estimate soil moisture globally and accurately. Another example is how, for instance, radioactivity ADOS map after a nuclear emergency can be improved by merging domain knowledge, local data collected with car or simply by walking around, or again, airborne surveys or satellite imagery. So actually, data fusion is very important in all applications, including food and agriculture. Finally, the ability to harness multi-sources data, including qualitative ones such as domain expertise, is also crucial. And for instance, a team at Wageningen University developed a prediction pipeline allowing, based on multi-sources quantitative data and expert knowledge feeding a Bayesian network, to predict very accurately food fraud events. So in this case, it is applied specifically to food fraud context, but such approach is widely applicable to many other domains, like, for instance, the monitoring of zoonotic diseases. So it's very interesting. So these three domains, so as a quick recap, analytical instrument calibration, data fusion, and data mining using multi-sources data are all very important applications for food and agriculture. So now, before I finish, I like to share with you three dimensions of the challenge ahead. The first dimension is data availability. So we mentioned open data policy several times already, but needless to say that when implemented, that's really a huge driver for AI development. Then the issue of data regulation is also very important to avoid, on the one hand, data misuses, but also as well to improve trust. Unfortunately, closed data policy and even sometimes regulation can hinder data movement. And there is an interesting AI deployment approach named federated learning, where instead of moving data to centralized repository using to train models, instead models are moved to the data. So such an approach might be used as a workaround, for instance, to data silos or bottlenecks. And it deserves definitely to be monitored carefully in the next months, years. The second dimension I want to put forward is the question of using AI to inform policies. Indeed, the lack of interpretability of AI model is often blamed and presented as the main limiting factor of AI adoption when it comes to informing policies. But actually, and that's also the case for the need to provide model uncertainties estimate or to assess model biases, the research is very active and the state of the art allow already many ways to, for instance, introspect models and to assess biases. So this kind of research is really quite successful and needs to be further supported and explained, disseminated to end users and including decision makers. Finally, the last point is the need for interdisciplinarity and interdisciplinary exchange. As usual, transdisciplinarity is not the norm. Opening the doors between disciplines is not the easiest step to take for several reasons. And often this situation leads people to reinvent the wheel and as well to miss opportunities to leverage the knowledge acquired by other disciplines. And this is all the more important when considering the frenetic pace of AI-related research. So in that context, knowledge transfer should be really fluidized. This is very important. And this is also the case of AI fundamental research, which has actually a lot to say, for instance, in developing more parsimonious approaches, in the ability to make AI less data greedy, less empirical, and in building theoretical foundation of AI. They are all of huge importance for the next following years. And AI is implemented in 10 years' time will be most likely very different from the one implemented today. So to recap, three dimensions of the challenge ahead for using AI in agro-food applications are first, data availability, second, meeting the criteria to inform policies, and last, fluidify knowledge between disciplines. So thank you very much for your attention, and I will be very glad to have the opportunity to pursue the discussion with you later on today. Thank you very much.
Well, thanks, Frank. I think you two touched on these challenges You talked about open data protection regulation, and you introduced today this concept of federated learning. And then I think most importantly, you just now talked about the importance of informing policies and fostering interdisciplinary exchange. And I think that's where these knowledge sharing platforms like the AI for Good can be extremely powerful. So I think also in this case, we'll come back to this in the panel discussion at the end. So I thank you again very much.
Thank you.
We move to the third talk of today, AI for Nuclear Science, from Professor Michelle Kuchera from Davidson College, USA. Dear Michelle, over to you.
Thank you. Okay. All right. So first of all, thank you to Matteo, and thank you for all of the organizers of this really great series. I've been asked to come talk to you about AI for nuclear science. And so I first want to give a background about what we mean when we talk about nuclear science. And so, so many of us are familiar with the atom, which is an atomic nucleus surrounded by an electron cloud. We are specifically talking about the center of this atom, the atomic nucleus, which is made up of protons and neutrons. And when people are studying the atomic nucleus, people study this at different scales. So perhaps we're studying the structure of the protons and neutrons themselves, the energy structure, spatial structure, stability, things like that. People also delve in and actually look at the structure of the individual protons and neutrons that make up of the nucleus. And so the inside of the protons and neutrons is, a much crazier landscape than people once thought. And people also study this nuclear matter in extreme conditions, such as high temperatures, pressures, things like that. Okay, so how do we study the atomic nucleus? Well, it is a very symbiotic interplay between theory and experiment. And so, so we have some physics that describes our underlying theory. We don't know everything yet. And we are trying to then execute experiments that can validate our fundamental understanding of the atomic nucleus. In order to do this, a lot of the experiments that we run are accelerator-based experiments. This requires us to then design things like detectors in order to look for the things that we are interested in discovering that relates to our nuclear theory. The end goal is to then really compile these databases of nuclear data that then are used in many industries and in society, including this data is used in all of the other talks that are happening today. And at this point now, artificial intelligence is being used in all stages of this fundamental research in nuclear science. So I'm going to talk about a few examples of some state-of-the-art work that's being done right now. The first example is an example in nuclear theory, where we are actually using machine learning or artificial intelligence methods to predict the probability of existence of nuclei. And so this here is a chart of what we call the nuclear landscape. And if we zoom in, we see that on the y-axis here is proton number. And so that's actually each element. So kind of like going across the periodic table. And theory is now making predictions using AI of what are the limits of existence, what is the most exotic type of nuclei that can exist, and then now new experiments are being designed and built in order to explore this region, these regions of what we call the nuclear landscape. Another example is then actually doing the experiment. So we have these theoretical predictions, and now we want to try and design experiments to compare them to these theoretical predictions. And so this is an example of using artificial intelligence to actually do the data processing and analysis. And so on the bottom right-hand side here, you see an example of a detector that's used to study nuclear reactions. And so we accelerate a beam of nuclei that then enter the detector. And there is then a reaction of that beam of nuclei with the gas in the detector. And then the detector itself can image in 3 dimensions the nuclear reaction that takes place. And then in the analysis, you want to be able to tag all of the products of that reaction to better understand what happened in the experiment. And so on the left-hand side here, you see us using artificial intelligence methods to actually do that particle-wise tagging of the reactions in this event. Similarly, we also can look at an entire event and kind of classify the type of reaction that happened with artificial intelligence. AI is also being used for detector design, and this is something that I think is really, really exciting because this specific example is for detector design for the electron-ion collider, which is a new accelerator that is currently under development, has not been built yet, and that gives us the opportunity to actually incorporate artificial intelligence methods from the very beginning, from the inception of creating this large facility, including the detectors. And so we want to detect nuclear reactions, and you know, these are not off-the-shelf type of detectors that you can buy at a store. The physicists and engineers have to design it. And so so how we're using artificial intelligence to help design our detectors is we use our theoretical predictions of what happens when nuclei collide. And then we start with some detector simulation. So some detector design, and then we say, what will those events look like in our detector system? And then you actually go through the analysis process as if it were a real experiment. And then the artificial intelligence algorithm can look at that analysis and make suggestions on how to improve your detector design to get out more meaningful physics. So maybe better data, more data, higher quality data, that sort of thing. This is an iterative process that is now currently being employed to actually work on detector design. Now, what's interesting and complicated about this optimization process of building an ideal detector is that we have multiple objectives. So it's not just a single type of thing that you're trying to maximize or optimize for in your design. So using AI for multi-objective optimization in detector design is a really exciting area that the AI is being employed for right now in our field. Also in accelerator operations. So of course, to get this, this beam of nuclei or particles into your experimental setup, we use accelerators to do so. And from the beginning to the end, so in the tuning of the beam, so actually getting the beam through the accelerator, diagnosing the beam along the way, and also setting up systems that will predict if a system is about to fail or has failed quickly in order to maximize the time that we're running these experiments is really important. And AI is currently being used and tested in all steps along the way in accelerator operation. So for example, it can be used to tune beams. So the idea is that you want a very localized beam so you can direct it towards your target to study a nuclear reaction. And so your starting beam may be very spread out, and then your artificial intelligence can actually tune your accelerator system in order to create that focused beam. And so we have a couple examples of that here. And one of the benefits, not only may your beam be more localized and more ideal, but it's also much faster. And so this is on the bottom is an example where an expert takes 10 to 20 minutes to actually get the beam in the ideal place through the accelerator, where our machine learning methods can do so in seconds. And that saves in the long run, a lot of time and enables more science to be done at these facilities. So what are the next steps? There's a lot of really interesting AI work that needs to be done to address some nuclear science drivers. So we've talked about a few real-time systems, so adapting to things that are happening during an experiment. And these are similar technologies as self-driving cars who have to adapt automatically to their environment. And so one more example of that is the Awake accelerator. And as you can see here, again, we're looking for a more focused beam and being able to adapt to the situations that it sees as it goes through the accelerator system. Uncertainty quantification is extremely important for us. Whenever we make a theoretical prediction, we need to accompany that with a confidence level. How confident are we in this prediction, especially because a lot of people are using the results that we're getting from analyzing our data in many other applications who don't directly access our experimental data used to get those. And so our uncertainty predictions are very important. And so our AI methods need to be able to predict those uncertainties with a robustness that we truly believe in those intervals. We really are looking towards established education efforts in AI. So already across the world in nuclear science, people have been investing in education efforts to really make sure that the future nuclear scientists and workforce has the literacy required. But we're really looking for something annual that can build an AI literate workforce, not just in one-off events, but continuously. Interdisciplinary collaboration and funding is also really important. So we really achieve the most. We can enable the most discovery in nuclear science when we're working in close contact with artificial intelligence scientists and experts in adjacent fields. And we need it to be this mutually beneficial symbiotic relationship where we can help inform AI method development, and similarly, they can help us with our specific challenges in the field. To that end, we really need to be thinking about interdisciplinary positions. And having the incentive structures in place for people that might be in such an interdisciplinary position. And of course, funding the research and development as it pertains to AI and nuclear science, but also taking that one step further and make sure that we have funding mechanisms in place to hire, say, software engineers to actually get this deployed and into production at our facilities across the world. And so this is the last slide where, the impact is really acceleration of scientific discovery for us. And there's a lot of little tidbits that AI really brings that all goes towards this goal. So of course, higher quality data, having these common data standards across the different types of facilities and subfields in nuclear science, having reproducible results, this all helps us really accelerate what we can learn about the atomic nucleus. And with that, I really wanted to thank all of the key contributors because, this work was really done in collaboration with all of them. So thank you.
Thank you very much, Michelle. You introduced today the need for developing workforce, and so the need of education. I think we're going to hear more from Christina also about this. So the importance of establishing this annual educational platforms. And then you introduced the idea of building AI literature, which I know we're going to hear also from Anna Benham when we talk about ethics of nuclear and AI, the importance of literacy. And then it comes back this AI being interdisciplinary, so requiring interdisciplinary coordination, and so platforms like AI for Good, and also what we had at the technical meeting. So maybe I think I can use these examples of drivers in nuclear science. You talked about the need for real-time systems and uncertainty quantification to connect with the next talk, because I think that includes nuclear fusion facilities. So now we'll hear from Dr. Cristina Rea. She's a research scientist at the MIT, and the talk is on advancing fusion research with AI. Cristina, over to you.
All right. Thanks, Matteo, for the nice introduction. Can you hear my screen? Can you hear me and see my monitor, I guess? All right.
Yes.
Okay, good afternoon, everyone, and thank you for giving me the opportunity of being here today to present a brief summary of how us in the nuclear fusion community are thinking of boosting our research progress through AI. So just a quick background, we are aiming at realizing a long-term clean energy solution that leverages nuclear reactions powering the core of our stars. In our laboratories on Earth, we are fusing hydrogen isotopes, deuterium and tritium, with the consequent release of energy through two different approaches. We are pursuing magnetic confinement fusion, which entails the heating and confinement of the plasma fuel through magnetic fields. And while the inertial confinement approach employs highly energetic beams, laser beams, to heat and compress a solid pellet of fuel target. Both the MFE and the IFE communities have produced so far a huge amount of experimental and simulation data, which lends itself to AI applications. Indeed, data drives fusion experiments from their design to analysis and optimization. Here I'm showing an example of how machine learning models, AI models, can actually be used to aid experimental MFE operations by combining simulation data and empirical one to inform scientists about the operational space that needs to be probed next in the following experiments. AI can indeed play a key role in science discovery. By exploiting these large data sets that are available, it can bridge gaps in our theoretical understanding through pattern recognition techniques and through the identification of missing effects, thus enriching our understandings of the underneath physics mechanisms. Similarly, in the IFE community, AI can be employed at different stages from simulation loops to experimental optimization in order to solve several physics problems. Inertial fusion involves also complex multi-scale, multi-physics systems, which can benefit from AI to unravel nonlinear couplings between such physics subsystems. It is important to also highlight how pushing the methodological development of such AI algorithms, a strong integration is also needed with the state-of-the-art hardware solutions, thus accelerators, GPUs, high-performance computing architectures. AI representations of physics packages lead to much faster computation when deployed on next-generation hardware. Going forward, AI will become an intrinsic asset of MFE for plasma performance optimization, event and anomaly detection, and plant operation monitoring. Here I'm showing an example of how the next generation of nuclear reactors might take advantage of AI predictive modeling for real-time monitoring of the plasma proximity to stability boundaries. To develop such data-driven solutions, interpretability needs to be preserved. We need to know why the plasma is going unstable. Therefore, black box models only have limited relevance for real-time action and control. A well-behaved output, a smooth output with well-defined validity regions and extrapolability boundaries is also mandatory. And for this aim, uncertainty quantification is essential at all stages to verify the reliability of AI-driven algorithms. These requirements all push fusion scientists to employ or develop the state-of-the-art AI solutions. Similarly to the MFE case, more computing power combined with AI solutions are allowing and will allow IFE scientists to elevate their predictive frameworks to improve modeling for both traditional simulations and AI accelerated models. Here I'm showing an experimental prediction pipeline that can correct simulation models using all fusion experiments from the last decade at NIF, the National Ignition Facility hosted at Lawrence Livermore National Laboratories in the US. The development of such pipeline entails the design of transfer learning solutions that can remove simulation bias, enrich simulations, therefore, by better matching also the experimental data themselves, thus improving the predictive accuracy of the models employed. However, the development of AI applications highlights existing bottlenecks in fusion that are actively preventing AI from fully accelerating IFE and MFE progress. To mention the most outstanding ones, Data accessibility is a first. We need big databases for AI model training and validation to develop our applications. However, there is hesitancy to share such data due to several issues, for example, laboratory ownership or security issues, intellectual properties. Such data can be actually patentable for patentable applications, or the fear of being scooped. We don't want to share often our data because our data sets, because of the fear that other colleagues might steal our research material and publish before we do. And we need to educate actually our communities to go beyond such barriers and gatekeepers. We need to invest in workforce development. And that's because hybrid curricula are needed in our community to fully leverage AI tools. Fusion subject matter experts need, therefore, reskilling in AI tools and for AI methods. And therefore, we need to invest in educating a diverse workforce, as we also heard from Michelle before. Last but not least, we need to invest more in community integration. We need to develop common frameworks to create one community of practice focused on AI for fusion that goes beyond just IFE and MFE applications or basic plasma science. So how can we address these bottlenecks and accelerate progress in fusion? Here, I'm suggesting a number of data-centric enabling activities, such as the development of open data repositories, the creation of cross-disciplinary institutes at our universities or national labs, the development of workshops and schools that can combine computational and data science elements with fusion research, or the active engagement of the community, of our community in new ways, for example, via Kaggle-like competitions or hackathons. And hidden in plain sight is actually the real need of a data steward, as Matteo mentioned before, to act as a broker or ambassador between the data and the user community, a role that may be played by international agencies, for example. Now, to expand on some of these topics, open repositories of fusion data should be made available beyond national barriers to fully boost AI-driven research. The status quo sees fusion databases hosted at different laboratories, at different facilities, behind firewalls in different file formats, and not connected. But AI for applied science and for fusion is a team sport. So problems are growing more complex and interdisciplinary, and the progress won't be made by individuals or small teams. So I'm borrowing here an encouragement that was given most recently by our colleagues, Brian Spears. So that's why we should actually invest in having centralized repositories of experimental simulation and plant operation data to allow us to build AI projects that can consume the data, opening up to participation to not just the fusion communities, but beyond the fusion communities worldwide. Additionally, we should educate our community to adhere to such open and fair principles. These foundational principles of findability, accessibility, interoperability, and reusability will serve to guide the data producers, not just to share only the data itself, but also the algorithms, the tools, the workflows that allow all components of the research process to be made available to ensure transparency, reproducibility of science, and reusability. So by ensuring open data access, the fusion community would be able to open up and engage an even broader interest in AI-driven applications. Open data access is crucial for attracting new talents and engaging AI community, and thus expanding our fusion workforce. Open databases, as I was mentioning before, can be used for outreach activities, workshops, schools, e-learning resources, and Kaggle-like competitions or hackathons. Thus allowing us to find creative ways to engage, energize, and integrate many different, many diverse members of the communities, from machine learning researchers to students at many different layers, from undergraduate to graduate students, to science researchers or interdisciplinary scientists, as well as partners from private entities, with a final clear added value, which is to bring all these small AI scattered activities worldwide and across many different institutions together. We can actually gain a critical mass, avoid the duplication of efforts, and exploit existing synergies to advance, to accelerate the progress in fusion research at a fast pace. All right, so I think I'm about to run out of the allowed time. So one last mention, the work presented in these slides aimed at summarizing the main threads developed at the Nuclear Fusion Working Group during the recent technical meeting, which was organized to explicitly set these directions for accelerating different fields' progress via AI. And so inside the Nuclear Fusion Working Group, we actually discussed potential community projects, calls for data, educational and outreach efforts, and all of this will become part of a final technical publication that will be made available next year, which I don't know if it was mentioned before. So I wanted to acknowledge the effort of all the organizers and the working group members, and thank you all for listening and tuning in today.
Thank you, Christina, and thanks for also sharing this important information about the report coming up next year, which is currently being drafted and developed. It's very interesting, of course, to see that when we talk about bottlenecks in fusion, we have data accessibility, workforce development, community integration, and these are actually bottlenecks across all other areas. So again, this is food for the panel session at the end. We're getting a few questions in the chat, and we're going to bring those with us in the panel session. So let's move to the final talk of today. Last but not least, we're going to hear from Professor Emma Rootkamp-Bloem and Professor Behnam Tahebi. Emma is from the University of Pretoria and South African Center for AI Research, and Behnam Tahebi is from the Delft University of Technology, and this is about AI ethics and nuclear applications. So over to you, Emma.
Thank you very much. Matteo, good afternoon from me in South Africa and from Behnam in the Netherlands. I want to say to start off with, and thank you for having us, obviously, and then also that it is necessary to understand that our focus on ethics is not in the negative sense. It's in a positive sense because we see ethics as an enabler of AI for good, of AI for atoms, and of atoms for peace and development. So please listen to us in that spirit. So we are going to talk to you about a new domain, which we have called the ethics of nuclear in AI, or NA. And so this comes from two fields, my field, which is Behnam's field, which is nuclear ethics. So the applications of nuclear technologies have given rise to certain ethical issues that to some extent have been discussed in the literature over the past decades. And then my area, the research, design, development, deployment, and use of AI technologies, including issues pertaining to big data and machine learning, have also given rise to emerging ethical issues. So an expert working group, which we chaired at the recent technical meeting at the IAEA, has looked into the existing concerns in both fields and investigated the extent to which the convergence of AI and nuclear science, technology, and applications could exacerbate existing ethical issues and open new concerns. So we will briefly discuss the state of the art in the ethics of AI and then in nuclear ethics separately, and then we will focus on highlighting convergent and main concerns in the ethics of nuclear in AI. If we look at the ethics of AI, AI ethics concerns may be divided into machine and computing ethics on the one hand, and ethical considerations of social impact of data-driven AI on the other. Basic subdisciplines include machine ethics, so focused on artificial moral agency, artificial personhood, data ethics, FAT issues, so fairness, accountability, and transparency issues, information ethics, focused on the quality and integrity of information and communication, ethics of social robots, human-robot relations, and then neuroethics, focused on mind uploading and things such as Musk's Neuralink and so on. So there is also, of course, a substantial overlap between the ethics of technology and the ethics of AI. Current hot topics, there are almost too many to mention, but a few: autonomy in terms of autonomous decision-making systems and social impact, fairness, bias, accountability and transparency, including explainability and interpretability concerns, artificial moral agency. Do we want artificial agency. We want algorithms to take life and death decisions in the military context or health context or even legal context. Data issues, privacy and data protection, data integrity and ownership. Speaking from Africa, a really crucial point for us. The quality and integrity of information and communication literacy, and I may add AI ethics literacy. The actionizability, effectiveness, and ownership of AI ethics policies, exacerbation of inequality versus the potential for benefit of all, the dilemma that ethics brings to that AI brings to us, AI technologies, and then robot rights and legal personhood for artificial agents. We quickly turn to the state of the art in nuclear ethics. The ethics of nuclear technology started in the 1960s and developed throughout the 1980s and 90s into the 21st century. The military past and major nuclear accidents such as Chernobyl were the leading factors. Subdisciplines in social sciences and humanities are international relations, for instance, first and second strike capability, radiation protection, for instance, of workers and public, ethics of technology, so for instance, values in designing new reactors, risk ethics, for instance, the siting of nuclear facilities, environmental justice, such as risk-benefit distributions, psychology in terms of acceptance, and then, of course, broadly, environmental studies. Hot topics in nuclear ethics at the moment: safety, including radiological protections, security, safeguards, including non-proliferations, environmental issues, including impacts of radiation on the environment, long-term protection, so in terms of intergenerational justice, and acceptance and acceptability of new nuclear technologies. So when we then finally come to the establishing the domain that we want to call the ethics of nuclear in AI, a broad definition of this domain, it is about reflecting on and the analysis of and suggestions to mitigate ethical concerns relating to the research, design, development, deployment, and use of AI applications and technology in nuclear science applications and technology. Some examples: the use of AI in decision-making and risk governance, the use of AI in nuclear reactor control, complementing operator control and automation, the use of AI to model and predict future reasoning styles, motivations, and methods, so intergenerational ethics, the use of AI in triage and diagnosis support in medical applications, and the use of AI in monitoring, dosimetry, and health surveillance after a nuclear accident, including links to phone apps. So focus areas of research within this new domain: autonomy and human oversight. AI technologies can and should never replace or have the last word in the ethical dialogue among humans. And I think this is important. It's very often people talk about autonomy and human oversight and say humans must always have the last word. That can in fact be counterproductive to innovation. But having said that, of course, there should be this don't want to call it a limitation, but the boundary that AI technology should not replace humans in ethical dialogue. Social justice and ethics dumping issues and environmental justice concerns, ethical issues of risk acceptability, awareness and literacy and public engagement, the responsibility gap, and regulation, the need for bottom-up approaches of engagement with all stakeholders, and then the urgent need for multi- and transdisciplinary research. So these are focus areas that come actually from the ethics of AI and from the ethics of nuclear side. So if we then now look to the new convergent themes in the ethics of nuclear in AI, risk, safety, and safeguarding is a big theme. AI applications can make for better nuclear risk assessment and better preparation, better pre-mortem analyses, better safety and safeguarding. There is a very, very strong theme around justice, and justice in many guises: social, distributive, retributive, epistemic, environmental, and needs a lot of further investigation from multiple disciplines. Responsibility issues, responsibility for harm may be even more difficult to assess in the ethics of nuclear in AI than separately. It's already an issue in both separate fields, but of course it is maybe intensified in this new domain. Impact on human agency. How do AI technologies challenge human authority and responsibility? Keeping in mind what I've said earlier. Bias and fairness, awareness of bias and finding ways to live or deal with it responsibly. We are humans, so from the side of structural bias, but the theme of bias and fairness also includes bias in terms of safeguards in nuclear applications, not just structural bias concerns in this new field. Also, the right to be informed. There is a new spin, maybe intensified spin, on fairness, accountability, and transparency concerns in AI ethics in terms of transparency in this new field. End users should know when AI in nuclear has been activated. Actionability of policies. How do we ensure impact of ethical considerations and enable all stakeholders to participate actively in such a broad domain? Responsible research and innovation, huge theme. And then some more like applied themes, 2 examples. In the context of climate change, AI, and nuclear applications, it may be interesting from within this domain, from an ethical point of view, to investigate the possibility of AI technologies positively contributing to informing the debates on relying on nuclear science applications, technologies, or ethics to solve climate issues. And AI in nuclear applications in medicine. AI applications can contribute to improving medical care and diagnostics, risk predictions, personalizing treatment, triage, and so on. So in terms of values that could underpin this new domain, some really, really preliminary thoughts. Values could be, for instance, respect and advancement of international human rights standards and principles, social and environmental justice and equity, non-discrimination and inclusivity, safety, security, and safeguarding on the one hand, and then robustness and accuracy on the AI side, recognition of the interconnectedness of all humans with each other and with the environment, which is maybe to some extent the way in which it's phrased in non-Western value, but very much important and needed to be heard. Human autonomy and oversight, and trustworthiness and credibility. Trustworthiness on the systems, on the technological systems, and credibility issues in terms of acceptance and respect for human dignity, etc. So the way forward, we would like to establish this new transdisciplinary domain and facilitate research and collaboration. We would like to provide training in this new domain for practitioners that is stakeholder validated. We want to facilitate science policy advice, ensure the quality of information and advice in terms of reflexivity and inclusive and deliberative character. We want to promote responsible research and innovation, AI applications pertaining to new technological innovations, including generation 3, 3+, and 4 nuclear energy reactors and fusion energy, and formulate maybe E&I guidelines, build a repository of best practice, work with UN agencies or organizations such as UNESCO and the ITU, as well as the Iaea. And then lastly, in terms of expected outcomes, we want to provide socially accepted and ethically informed decision-making regarding AI applications in nuclear science, technology, and applications. We want to create awareness among practitioners, governments, and members of civil society about the ethical implications of AI technologies, nuclear technologies, and applications, and the convergence of these fields. We want to enhance, facilitate, and sustain dialogue with important societal stakeholders. And we want this field to contribute to the safe, secure, and peaceful application of AI technologies in nuclear science, technology, and applications. And as such, among other benefits, aid progress towards the United Nations Sustainable Development Goals, such as SDG 16, peace, justice, and strong institutions, and 17 partnerships for goals. So thank you very much. And thank you also for the team that worked with us during the technical meeting.
Thank you, Emma, and thank you, Benham. It was extremely, I think, interesting to hear this focus area of the ethics of nuclear AI. We could see there's social justice, ethical issues of risk acceptability, autonomy, and human oversight, and then literacy, regulation. And then we heard some preliminary thoughts on the values driving the ethics of nuclear AI. And I think this is the perfect stage for to hear these values. And since the AI for Good aims to promote action-oriented dialogue, I think this can be also a perfect opportunity for us to see what can be done for turning those values into action. So let's talk about this in this session, which follows now your final talk. So we had some questions from the chat, and then I have also some questions for all of you. So let's start from there were a few technical questions, and one of these is for all of you. It's from Arn Lutman. So thanks to all the speakers for their excellent presentations on applications of AI. Would it be possible to provide some examples of the specific types of AI machine learning in terms of algorithms or architectures that are being used in these examples? So maybe we go in the same order. We start from Georg.
Sure, thanks. So I think it's a very good question. I think there is a very wide variety, but I think that the most often used architectures are convolutional neural networks for the classification, autoencoders for unsupervised learning, and more recently, architectures such as generative adversarial networks have proven to be really very powerful in kind of capturing the variability that we see in the imaging data. So these are the main architectures that we are working with, and tools, PyTorch, TensorFlow, these types of open tools are most often used in our field.
Yes, Frank.
Yeah, so we are more or less on the same time. And we are heavy users of convolutional neural networks, all sorts of kind of architecture, and so the food fraud prediction pipeline use Bayesian network, as you saw, and we on the our research and development side of all, we are very much interested in generative adversarial networks, autoencoders for data augmentation. So yeah, in summary, we use essentially convolutional neural networks and Bayesian networks. Yeah.
For nuclear science, of the examples that I gave, of course, we use so many different methods, but of the exact examples I gave for the examples that had uncertainty quantification with the predictions, we used Gaussian processes and Bayesian neural networks. We use some interesting point cloud-based networks. So they have these more newer like point convolution operations in them to deal directly with data in our detectors. We also use standard convolutional neural networks when we can treat our data like images. And we use generative adversarial networks, normalizing flows, and conditional versions of both of those a lot as well. So I hope that helps.
Well, I guess I would be redundant saying that we use all of the tools mentioned so far, really depending on the type of data. Image data or lends itself to the use of convolutional neural networks. For example, we do lots of time series predictions with recurrent networks or UNets, but we also leverage more classical machine learning methods like random forests or support vector machines, which they always find, their use for a more simpler data, for a simpler data scope. And since we are also interested in extracting the underlying physics and an analytical formulation of such boundaries to instabilities, we try to use also symbolic regression, for example, and those methods will actually help us define these metrics to the classification boundaries.
Okay, so there's another quick technical question. I think we can take it. What, if any, challenges do you face is scaling your models across both on-premise and cloud infrastructures, especially in the cost of moving and working with data across both? This is from Justin McCall. Any of you wants to take a stab?
Well, I can start. Can jump in. So. As fusion scientists, we tend to do lots of work in-house on computational servers that are hosted at different laboratories, or we try to allocate wall time on big computers and computational architectures available, for example, in the US, like NERSC or El Capitan, other big, architectures. Challenges of data moving, something comes to mind. Colleagues at Princeton, for example, have been working a lot with experiments in Korea and South Korea, and they are able to move around experimental data from the experimental device in Korea to NERSC in the US, perform on-the-fly analysis, and then inform back the experiment on timescales useful to run the following experiments. So we're talking about data moving and about minutes. So it takes minutes to run the experiment, perform on-the-fly analysis, and then move back the data around. So and all these pipelines are actually created in-house by fusion scientists with a hybrid background in machine learning and AI. So that's we are not just exploiting products that are available on the market, but we are investing in discovering new tools and methodologies ourselves.
Any of you would like to complement, or I can move?
I can add one thing. I think that was a good discussion about moving data. I think another big challenge, at least in the nuclear science side, is actually the lack of data standards. So typically we present data to these machine learning models in a way that's not directly how the data is, say, coming out of the detectors or how we're used to dealing with it. And so sharing models across different research groups or facilities is a lot harder without that data standard of being able to present our data the same way to these models.
Okay, I have a question now. I thought we could quickly go around. So I was thinking maybe I'll be curious to know if you had to remove one of these challenges. So you all had listed sets of challenges. If you could remove one, which one would that be?
Should I go ahead? So definitely the one that Michelle just mentioned, like this issue about data standards and all and different data formats. And again, I mentioned really how open data would make things more easier and boost progress in fusion science worldwide. So it's I see this every day, and different groups are reproducing their own data sets, maybe reinventing the wheel, and that's because there is not openness or a lot of communication happening between the different groups, and yes, we would need to leverage probably international agency to manage those data embargoes or establish common formats, or at least provide us with the tools to communicate and better share our tools and data. So I'd say open data.
I have one. So I think like for us, we are working with personal data, with patient data, and very often it's really hard or impossible to anonymize it. So it kind of stays patient-related or person-related data. And so there is the the data protection issue. And there is legislation now all across Europe and also in the US that kind of structure that makes it very clear what's possible and what's not possible. But in practice, we very rarely reach what would be possible because of legislation, because the real blocker is not so much what's possible legally, because you can share data if you have the corresponding protection, but very often it's the trust with whom you share data and the governance infrastructure, the governance structure that is built around the data. And so I think institutions and organizations like the United Nations and the Iaea and ITU, I think you are very well, positioned, because there is a lot of trust in you in order to help with that, in order to kind of build systems of governance or systems of data sharing and data pooling where there is trust, so that we can pool the data and work on the data. And it's really critical to work on not data from individual centers, because we learned that in order for these models to really work and to benefit lots of different patient populations, we also need to train and validate with these patient populations. So I think that's the main blocker right now, that the ability to share data because of trust and governance.
Yeah, so very well. I think this connects exactly what one of the focus that we had at the technical meeting, which was road mapping the possible role of the Iaea, and today, in fact, we're looking at from a broader angle what could be what is the role of international organizations in this, and so I think data stewardship always comes as one of those possible enablers. And in fact, I think platforms like the AI for Good and the technical meeting itself can be great in informing policies and providing this cross-domain coordination. But then I think we need to also start thinking about more focus activities. I know that the ITU through the AI for Good has this. We just heard also during the opening speech by Director Lee, we heard about this focus groups. So maybe this could be one of the way forward also within the AI for Good. Perhaps in next sessions or next year we could dive more into specific areas. And the same can be said for the ethics of nuclear and AI. I see Benham has raised his hand, so. Please.
If I may just add a quick point regarding which challenges to overcome. I think you mentioned a couple of times actually throughout the introductions, but also throughout the talks, that the necessity of working in an interdisciplinary fashion. And I think that's also a huge challenge that needs to be taken on. Because you were asking, for instance, a question about methodology earlier on. And I can tell you when social sciences and humanities are collaborating with engineering and sciences, method is a very important issue because there are different methods. There's different language, different vocabulary, and different concepts. So I think I see a crucial role here also for the IAEA to facilitate this kind of interdisciplinary collaborations on the one side, social sciences and humanities, and the other side, sciences and engineering. So this is, if I may add one more thing to that list, this would be definitely the one.
I'm going to jump in because I didn't understand that the question was for us too, but I just want to say I couldn't agree more. And it is, when we talk about interdisciplinary or multidisciplinary work, we don't mean necessarily only, or shouldn't mean only, within the mathematical sciences, within the physical sciences. We should mean across the broader disciplines. But for these conversations to work, there needs to be openness and understanding that methodologies differ. And that's why we think, Benham and I think of ethics as an enabler for what it is that all of you want to, that all of us want to attain. Thanks. Ben, I'm jumping on your back, but thank you.
Okay, well, I think fantastic. We're on time, and I'm glad that I think we touched upon all the main aspects, and I think we can also say that we have a sort of promise to meet again in the near future. Also here in this within the AI for Good, and to focus more on some of these topics of today. So I think I can hand it over to my colleague Reinhard.
Yes, thanks very much, Matteo, for curating, moderating, engagingly the session today. So before you drop off, everyone, if you could fill out our survey, our satisfaction survey, my colleagues will put it up, the Net Promoter Score. Check one of the boxes on whether you are likely to recommend this webinar to a friend or a colleague. So while you do that, so we hope that you can join next Wednesday's session on AI for nuclear energy. On the 24th of November, we have pretty much daily programming on AI for Good with technical in-depth talks. So if you are curious, please check out our website, aiforgood.itu.end. And with that, I wish you a good day. Bye-bye.
Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector.